My topic focuses on the differences in graphing Allee effect with respect to equilibrium solutions and integration. First off, you need to understand the history with Allee effects, so how it evolved from other math models before it. First is you have your exponential growth. This is when something grows without bound. This is typically fairly limited as only newer populations use this method or model. So you need to improve upon it. The next improvement was done with Velhurst. He found the logistic growth, and this includes a carrying capacity. This is a limit that if it exceeds the limit, it will come back down towards the carrying capacity, and if it is below the limit, it will increase up to or close to the carrying capacity. This, however, still does not account for all of the different impacts that populations may face, such as requiring a certain genetic diversity for a population to survive, and this is where Allee effect can come in. Allee effect has another threshold, the Allee threshold. If it is below this Allee threshold, it will go back down towards 0, so your population would diminish. This still includes the carrying capacity, so if it is above that Allee threshold, it will increase back up to the carrying capacity. This was found by Werder-Clark-Allee. Here on this next slide, you will be able to see my different equations for exponential, logistic, and Allee effect. Here you can see that certain aspects of the differential equation are carried on into each equation. However, you see that each one has an added variable. Therefore, that shows that you can have more criteria or more requirements for each population. Allee effect has two different types. First, you have weak Allee effect. Weak Allee effect does not have a hard limit, so therefore, if a population is under the Allee threshold, it will slow down up to the point, but it will not decrease. Strong Allee effect, conversely, does have that hard limit, so it will decrease back down towards a diminishing population and 0. This relationship is illustrated in this graph. As you can see that when the only graph or equation between logistic growth, strong Allee effects, and weak Allee effects that is a negative population growth rate is strong Allee effects. The significance of Allee effects is in dealing with population modeling. So population modeling has been looked into with Allee effects for predator-prey relationships and with respect to environmental rehabilitation. So you can look and see how that would increase the levels, but if it was already under that threshold, how it may not affect it at all. It may still be on the decline. Additionally, Allee effect has been looked at with respect to epidemiology. Epidemiology is the study of the spread of diseases or illnesses, typically between individuals, but it can also be within the body. Allee effect has specifically mainly looked into cancer research. It has looked into how when the cancer cells are close together, that is better for the spread of cancer. So when it's further apart and therefore has a lower population, it can be more effectively on the decline, and therefore it can look into how and when the treatment needs to be implemented for a better likelihood of treating the cancer. Finally, there is economic policies. So this is more limited and is indirect, as Allee effects has been used to look into agriculture. This agricultural standpoint has been showing how you can plan your business or your profit margin around the crop output you have and predict that crop output for the next year. Then you get to the gap in knowledge. The gap in knowledge is between different methodologies. For Allee effect, you have 3 different main methods: integration, equilibrium solutions, and formal power series of Poincare. Formal power series was excluded from my study as it is used in complex algebra, and the other 2 focused in on calculus-based. So these 2 calculus-based methods have not been looked into with respect to the same article or the same journal, and therefore that is where the gap is. the gap is in the differences between the two methods. This leads to my research question of, do the methods of integration and equilibrium solutions differ when creating the graph from a logistic growth formula with strong Allee effects from its differential equation? If so, how do they? My initial hypothesis is that the number of steps and the number of intermediate products between each will differ. So the implications of my research first have to deal with what method is better to teach to beginners or to for the basics of calculus. As certain methods, it has been shown that if you have a visualization technique or a graph, it would be more effective to teach, as it can help those that find the math harder to grasp, and therefore that is one implication. Another implication is for specific research goals, it may be better to have a general graph instead of a more specific graph. This leads into my methodology. Overall, mathematics is an overarching method, but each of these two, equilibrium solutions and integration, is a method in of themselves and will be looked into with respect to a general example and a real-world example. The general example will show, without specific variables, the general processes that each step takes. And the real-world example will take into account specific variables and will show the steps thoroughly and for a final result. So one assumption that you have to take is that I will be using positive constants and positive coefficients, as the positive constants deals with you can't have a negative population and you can't have a negative time, and along with the positive coefficients, as if you changed the sign, you would change the pattern that the graphs would follow. Then you have my delimitations. First off, I am only focusing on strong Allee effects, as weak Allee effects would require partial differential equations. Additionally, I'm only focusing on the two methods, as I left out formal power series of Poincare. So here I will define my variables that will be used in the next slide. First, you have your P of t, or your P, which is your population. Then you have your L, which is your carrying capacity. Then you have your B, which is only really used in your logistic growth formula, not your differential one, but your original. This helps you find your midpoint. Then you have your K value, which is your intrinsic growth rate. Your T, which is your time. Your dP over dt, which is your population growth rate. Your A value, which is your Allee threshold. And your C value, which is your constant of integration. As when you integrate without specific, you're getting a general solution, and if you don't include your C value, you're getting a specific formula. Here you can see some of those variables in use in the Allee effect differential equation. Here's my real-world example. My real-world example deals with passenger pigeons, as passenger pigeons have gone extinct and have been used in different models for the Allee effect. The information that you need to take from this in order to see my steps in the next few slides are the growth rate of 30%, the carrying capacity of 8,000, and the individuals required for the population to survive, or the Allee threshold of 1,500. I'm going to be scaling my graph with respect to the thousands, so the 8,000 individuals will be taken as 8, and the 1,500 will be taken as respect to 1.5. The first step involves plugging in these variables. So you get your first step, which is your equation. Then you can find your equilibrium solutions, as this will be when your differential equation will equal 0. That is when your carrying capacity of 8 or your Allee threshold of 1.5, as shown in the graph. These are your horizontal asymptotes. Finally, a slope field. A slope field is a graphical representation. It includes line segments that have a slope at that point where the solution is equal to the differential equation solution at that point. Here is step 3, 4, and 5. Step 3 is numerous lines, as I counted these steps together when it was just distribution. So those were counted in one step. And this is when you're trying to plug in your p-value to get your slope for a specific point. Step 4 is plugging in your slope to a slope-intercept form. And step 5 is finding your intercept. This will give you, after multiple repetitions of that step, your slope field. Once you have your slope field, you can plug in an initial value. For this graph, the initial value was 1,250, or 1.25. So therefore, it is under the Allee threshold and decreases back towards 0. I also included another one with a initial value of 4,000 people, or 4. And that is over the Allee threshold but under the carrying capacity, so it increases up towards the carrying capacity. Then there is integration. You have definite integrals and indefinite integrals. So definite integrals is when you're looking to find a specific value such as an area or a volume, and an indefinite integral is when you're looking to find an antiderivative, which is more general formula. For integration, step 1 through 5, you have 5 lines, which is because each of these is a different step and not just distribution and simplification. This is going from your differential equation to an equation that can eventually be graphed, and your step 6 is your distributing and getting down to that final equation that you can plug into your graphing function. Then you have to plug in your initial value. So you have your initial value of 1.5 again, and you can see it decreases back towards 0. And here you can see it increases up towards 8 with an initial value of 4. So overall, the counts for total steps and shared steps are fairly close, whereas the total graphs and intermediate graphs have a fairly similar, but difference with respect to the proportionality of the numbers. So since I have only one data point per each category, I could not run a statistical analysis as the data was perfect and it only had one category, or one data point per category. So therefore you can do percent change and percent difference, because these look at the difference with respect to the proportionality and size of the numbers. This gives me my results of total steps has a percent change of about 14% and a percent difference of about 13%, and my shared steps have 0% for both percent change and percent difference, whereas my total graphs has a percent change of 66% and a percent difference of 100, and my intermediate graphs have a percent change of 100% and a percent difference of 200%. This means that the total steps and shared steps don't really have much difference, but that the intermediate graphs and total graphs do. This supports part of my hypothesis, but not my full hypothesis. It supports the part that shows that my my intermediate graphs will differ in counts, but it disproves the part of my initial hypothesis that shares that the total steps will be different. They are the same, so that is discounted. The implications of this are that with equilibrium solutions, you have more graphs and therefore more visualization. So it is likely assumed that equilibrium solutions would be the better method to teach to beginners, as they can see the general patterns even without an initial value and more. Some of my limitations are the lack of significance tests, as it is open to interpretation, the numbers. My percentages, while they do show kind of a disparity or a non-disparity, that does not show significance, as it is open to interpretation whether you believe the 66% and other values are significant or not. Additionally, it is the lack of generalizability, as I only focused on strong Allee effects, so weak Allee effects is not included. Future research could look into how the equilibrium solutions, is it actually more effective in teaching? Because I only focused on the two methods and not its application in teaching. Additionally, it could be looked into for different research goals if intermediate graphs are used or can be used. And since I found only the patterns and trends for strong Allee effects, it would need to be researched further to see if weak Allee effects followed a similar trend with the same methods or if it followed a different trend.
All right, so how did your initial exploration of the scholarly conversation lead to your final research question or project goal?
So originally I was focused mainly on general math methods. I didn't know which one I wanted to focus on. So I contacted my expert advisor. He gave me a couple different examples of different math models, such as the one that's used in enzyme catalysis, one for action potential in neurons, one for determining the time of death based on lividity and Allee effects as well. I determined that Allee effects may be the best one for me to look at, as it was a continuation or an enhancement on something I learned in AP Biology the year prior. When discussing Allee effects with my expert advisor, we both showed different methods of getting to it, so when I was reading the scholarly material around Allee effects, I focused in on the methodology, and while observing that, I found that none of them looked at two methods at the same time, therefore leading me to my gap and my research question of how these two different methods differ.
Thank you.
How did the limitations of your method or data influence your new understanding?
So some of my main limitations are that it is only applicable to strong Allee effects. That means it's not generalizable in the fact that when talking about my new understanding, I cannot generalize it to all of Allee effects, only to specific strong Allee effects. Additionally, the only two methods means that when you're looking into multiple methods with the Allee effect, if you're asking which one's better, you have to take into account that mine did not include formal power series, so that may not be the best representation of that. Additionally, the lack of significance test limits the significance of my results, but the numbers and percents can be open to interpretation of percent change and percent difference, and that can leave open an avenue for other researchers to still use my data while being cautious of if it is actually significant or not.
Think back to your initial curiosity that sparked your inquiry. What other curiosities do you have, and how has this process prepared you to explore them?
So, my initial curiosity that sparked my interest, like I said, was looking into general math models. Specifically, I looked into Allee effects, but all the other models are also really interesting. In my differential equations class, we learned a bunch of different math models, and I'm going into an applied mathematics major. So with that, I can take all of what I've learned and how to format these equations into my future career and my future college aspirations. In that, I can learn to focus on other general math models, and I now know how to format them and to write a paper on them and to involve the help of my expert advisor as well.
Is the additional question?
I feel like she kind of already answered that one. If you could revisit your research process, what would you do differently and why?
If I could revisit my research process, I would probably include some qualitative data, mainly on the types of steps instead of just the counts. So if it was more calculus-based steps or if it was more algebra-based steps, because that could take into account the difficulty or lack of difficulty of certain methods. As when looking into how equilibrium solutions is effective, if it's a harder source, it may not be as effective in teaching. this could add a dimension to my results and to my study.
Thank you.